Hello students, in this video I am going to explain you magnetic field of a long straight solenoid. Let us start the video. Solenoid is a long cylindrical helix made by winding closely large number of turns of insulated copper wire, and magnetic field lines are produced around and within the solenoid when current is passed through it. Let us see here in the figure. Here a number of turns of insulated copper wire are wounded in the form of a helix, and if we see carefully, the direction of the current is downward in all the loops. Let us draw one loop separately. Let this be the loop, and the direction of the current is downwards. So this appears as a circular loop carrying current. So definitely magnetic field will also be produced. Let the magnetic field direction will be somewhat like this. If we have placed a number of loops nearby, then they all will be producing their magnetic field. The magnetic field of one loop will get linked to the magnetic field of the other loop, and there will be least spreading of the field lines like this. They are placed close to each other, so the magnetic field will try to link with the other loop. But as these loops are placed very close to each other, so these magnetic field will have least spreading, and the magnetic field lines will align themselves parallel to the axis of the solenoid, and we will form a uniform magnetic field as shown here. And the direction of this magnetic field will be given by curled straight right hand rule like this. If we grasp the solenoid with our right hand such that the fingers are curled in the direction of the current, see here the direction of the current is downward, so we have to arrange our right hand in such a manner that the fingers are curled in the downward direction. So the extended thumb will point in the direction of magnetic field like this. So this will be the direction of the magnetic field, and they will form closed loops like this, and the field lines are produced as in the same way we have with our bar magnet. Now let us consider a longitudinal section of the solenoid. See, we have considered a long solenoid as its length is large as compared to its diameter, so the magnetic field outside will be small as compared to the field inside the solenoid. There is a uniform magnetic field inside the solenoid except at the edges where the spreading of the magnetic field takes place. So consider a rectangular path ABCD as shown here, where AB is parallel to the axis of the solenoid, BC and DA are very long and perpendicular to the axis of the solenoid, and this CD part is very far from the solenoid, which is having negligibly small magnetic field. If you view carefully, there are dots and crosses here like this. The dot represent that the current is pointing out from this side, and cross represent that the current is pointing in from this side, as we have seen in our earlier figure like this, and the current is from top to bottom. Similar is the case here, current is from top to bottom. Now let us consider Ampere's circuital law. According to Ampere's circuital law, line integral of B dot dl is equal to mu naught times the current enclosed by the rectangular path. Here the rectangular path is ABCD, so the current enclosed is represented as I dash. So the line integral B dot dl of ABCD will be separated in 4 different line integrals, that is from A to B, from B to C, C to D, and then from D to A. If we look carefully in the earlier figure, BC part and DA part both are perpendicular to the magnetic field. Let us see again. This is BC part and this is DA part. Both are perpendicular to the magnetic field. That is, the direction of these line element and the magnetic field is 90 degrees. So these two elements will give us 0, and the magnetic field outside the solenoid is, we have already considered as 0 because it is at a very far distance. So the line integral of the rectangular loop ABCD, out of the 4 parts we are left with a single line element AB, that is only this part is left and all 3 parts vanishes. Now in this part AB is aligned along the axis of the solenoid, and the magnetic field direction is also along the axis of the solenoid. So the direct angle between B and DL is 0 degrees. So it will come out to be B line integral of DL, where DL is the length of AB part, which we have considered as X. So in Ampere's circuital law, the left hand side of the equation becomes B into X. Let us mark it as equation number 2. Now see the right hand side of the Ampere's circuital law. Let N be the number of turns per unit length of the solenoid. Then the number of turns passing through the rectangle ABCD will be N times X, because we have considered the length as X, and the current flowing through the solenoid is I. So the current enclosed by the rectangle ABCD will be Nx into I, that is I dash will be Nxi. Mark it as equation number 3. Now putting the equation 2 and 3 back in equation number 1, that is in Ampere's circuital law, we have obtained this equation, that is Bx is equal to mu naught Nxi, where B is equal to mu naught Ni, that is we have cancelled X from both the sides. So this is the magnetic field within the solenoid, and if we want to calculate the magnetic field at one end of the solenoid, it will be half the magnetic field inside the solenoid, that is mu naught Ni upon 2. Thus magnetic field is independent of the length and diameter of the solenoid and is uniform over the cross section of the solenoid. Thanks for watching. Please like, share and subscribe.